Alright, so we'll do a horizontal hyperbola for this one. And the horizontal hyperbola, the formula would look like this. Well, let's just draw the template of a hyperbola. A hyperbola is always equals 1 and it's minus. It's opposite of the ellipse. Underneath, on the denominators, a squared is always first and b squared is always second. That's different from the ellipse. The ellipse says that it doesn't matter where you put these. But here it matters. Why does it matter here? Because of the subtraction sign. It's not commutative. Okay, so you guys said you wanted a horizontal one. So what are we going to put above the a squared? Yes, it's a good guess. The x is horizontal, so that's what you want above the a squared. Whatever's above the a squared, just like the ellipse, whatever's above the a squared, that's what tells you if it's horizontal or vertical. And so the y minus h would go right there. And that is a horizontal hyperbola. And a horizontal one would mean that...
You mean y minus k.
So I put in... thank you. So that should be y minus k, not h. Now, if it was... if it's horizontal, that means that there's a horizontal line that's called a transversal, and at the end of that horizontal line, you're going to put vertices, and you're going to draw your hyperbola, and your hyperbola looks like that. It's two parabolas, and it's a little more in depth. We don't just draw random ones. And vertical would be vertical transversal. You put vertices at the end of that, and your hyperbola would look like that with two parabolas on it. So let's get specific and see what this looks like. Now I want to do one centered at the origin again. So that means we don't need the h and the k. So we'll get rid of the h and the k. But I need an a squared. Can someone give me an a squared?
9.
9 sounds good. 9 is perfect actually. And for the b squared, I'll put 16. You guys notice something different here than the ellipse? Yeah, the a squared is actually smaller this time. Can it be bigger? Oh yeah, it could be bigger. It could be smaller. Here it doesn't matter. The a squared is always the one that's not negative. B squared is always the negative one. Alright, so let's clean it up. It'll be x squared over 9 minus 16 on the bottom and y squared on the top. That equals 1. Alright, our center is right here at the origin. That's our hk. Where is my vertex? Where are my vertices going to be? Now, because the a is right there, and because it's 9, that means, a squared equals 9. So what is a?
3.
A equals 3. So that's how many spaces you're going to count. 1, 2, 3 to the left, and 1, 2, 3 to the right to find your vertices. Now I'm going to erase this because it's kind of in my way now. So I have a vertice right there, and a vertice right there. Those are my two vertices. Now, a hyperbola doesn't really have covertices, but I still call them covertices because it makes it easier. I need to find points above and below. Okay, so b squared equals 16, and that means b equals 4. So how many spaces am I going to count up and down?
Up 4.
So that's my covertice, which doesn't really exist. 1, 2, 3, 4. And there's my covertice. Now we need all these points because it shows us how to draw a box. And we need this box. Like, why do we need that box? We need that box. This box helps us draw the asymptotes. There are asymptotes for the hyperbola. The asymptotes go like this. They go through the center. Oops, I forgot to be recording on that one. So I just explained to you guys how to find the asymptotes. We used point slope form, which is y minus y1 equals m times x minus x1. Okay, but instead of y1 and x1, we use h and k. And in this case, h and k are both 0 because our origin is our center right there. So I could put a 0 there and a 0 there. And then to find our slope, we just have to count the slope. For this line right here, we would count the rise and the run. The rise is 4, the run is 3. and so that's 4 over 3 for that slope. And then for this line right here, to count the rise, we would go down 4, which is negative 4, and then right 3. So that'd be negative 4 over 3, which is why we have plus or minus 4 over 3. And then we simplify it to get to look like that. Alright, there's one more thing we have to find. And I'm going to press pause so I can erase stuff. The last thing we have to find are the foci. Now, we know that our lines are going to go like this and like this because our vertices are right here. That means our focus points are going to be somewhere right here and somewhere right here. In order to find the focus points for this one, what we have to do is we have to take a squared plus b squared equals c squared and find the c. The c tells you the distance the focus point is from the center.
Wait, I thought we were doing horizontal, not vertical.
This is horizontal.
Yeah,
If it goes like this,
that it's B.
if it goes like this, it's horizontal.
Yay, look at the one.
Okay, so this is the formula to help you find the c. Notice that it's different than the ellipse. The ellipse had a minus sign right here. I remember because the hyperbola has a minus sign for the standard form, and so that means for the foci, I use the plus. All right. So to find this one, my a squared is, what's my a squared? 9. My b squared is 16. That equals c squared. 9 plus 16 is 25. Dang, you guys pick pretty numbers. What is my c? It's 5. And so we're going to count 1, 2, 3, 4, 5 that way. 1, 2, 3, 4, 5 that way. And we have our focus points. Now we can graph our line. Now you just gotta follow the asymptote. Make sure you hit the vertex. And there you have it. That is a hyperbola. Oh, and on my formula sheet, guys, I messed that up. I think for the foci, for a horizontal, on the hyperbola sheet, I think I messed that up. It's supposed to be h plus or minus c k. Which makes sense, because we're adding and subtracting, we're going left and right to find our focus points. We're going this way, and then we're going this way on the x. The focus point right here is, I think it was, oh, this is not, okay, it goes like this. It goes from this distance, and this distance. It's kind of the same like with the ellipse. So from the focus points to the points that are on the graphs, like this point right here, this distance and this distance
Are the same?
are not, they're not the same, but they make the Pythagorean theorem.